We have a salt that contains cations, iron 2, and sulfate, anion. So we determine that we have an alkaline gas that is produced, which will be ammonia. Sulfur dioxide is acidic, so that will be out. And then a gray-green solid is formed. This is because the iron 2 reacts with your sodium hydroxide to form iron hydroxide. So these are the identities of the gas and the solid residue. (14) is a very common question. It's just usually they give different values for different years of papers. So we have nitrates decomposing and 1.53 grams of gas produced. So be familiar with nitrate decomposition. We have oxides, NO2, and oxygen gas. So 1.53 will be for here. We take the difference, originally 3 grams, subtract by the gas, we will have 1.47 of the solid remaining. And then we'll use these two comparison. We know that 2 moles of nitrates will give 2 moles of the oxides. So we try to change this to a number of moles of nitrates. 3 divided by the MR, X plus NO3 times 2. Then we take this mass, divide by MR of X oxide. Right, and then we say these are the same moles because the ratio is the same. Once we equate this, we have an equation to solve. I will not show you the steps, but for this question you get about 87.8. That means your X, if you refer to the periodic table, will be strontium. If you run out of time or you can't remember how to solve equations, just substitute the respective MR of your metals into X and see which one gives you the equation. 15. Change in oxidation state of the element that is reduced. The elements in focus are sulfur and the iodide, so we can do a quick comparison. Sulfur plus 6 here, plus 6 at the end, and it becomes minus 2. Iodide minus 1, oxidized to 0. So it is the sulfur that we are interested in. Plus 6 to become minus 2. You have to change by 8 units. (16) We need the rat poison to be insoluble in water but soluble under acid conditions. So if we compare the options that we have, we know that carbonates dissolves in acid but is insoluble in water. So that's the criteria that we are looking for. Barium chloride soluble in both water and acid. Barium hydroxide also soluble in both. Sulfates insoluble in both, so doesn't fulfill our criteria. (17) A bit of recall question. Haber process, you know that you need 1 mole of ammonia and 1 mole of nitrogen and 3 moles of hydrogen, and then the catalyst is finely divided iron. So it's B. (18) Which oxide when mixed with water will produce lowest pH? Now, sodium hydroxide will give us an alkaline solution. Right, so that one is out compared to the acidic ones. Silicon dioxide, you have to know, is insoluble. So actually when you throw inside water, its pH is actually 7. It is acidic, but you react with base. It doesn't dissolve in water. So it's between phosphorus or P4O10 and carbon dioxide. This is mildly acidic. P4O10, if I use the equation on top, you can see that it's actually produced quite a bit of acid, phosphoric acid. So this one has the lowest pH. sulfur trioxide, water and ammonia, we get ammonium sulfate. What does not occur? Well, this is an acid-base neutralization, acidic base. So this is true. Dative bond, your ammonia gas has a lone pair. It accepts a proton to form NH4 plus. So there is a dative bond forming. There is an ionic bond between your ammonium ion and sulfate ion. Right? There's no oxidation or reduction. You can check any convenient one. I use sulfur as example. +6 here. And this is actually +6. So there's no oxidation, no reduction. Organic compound acts unaffected by hot potassium manganate but reacts with acid in the form of or in presence of concentrated sulfuric acid. So I put this condition as 1 and 2. We have esters, ketones, tertiary alcohol and secondary alcohol. Right? And ester, some of you might think is not affected, it can't be oxidized. That is partially true, but don't forget the presence of acid will hydrolyze ester. So the acid hydrolyzing ester, it just means it will be affected by number 1. So statement 1 doesn't apply to ester already. Okay, so that is out. Ketone, not oxidized, but ketone won't react with ethanoic acid. Tertiary alcohol will not be oxidized, but it may react with your ethanoic acid to form an ester. So these two statements apply for your tertiary alcohol. Secondary alcohol, it can be oxidized, so it will be affected. So it is your tertiary alcohol. Will not be oxidized, but can form an ester. (21) Sigma bonds and pi bonds. Sigma bonds will be your single bonds. Right? Pi bonds will be what is on top of a single bond, or built on top of pi single bonds. So we have sigma bonds and pi bonds here. But it is dangerous to just look at this structure. Don't forget the carbon and hydrogen also has single bonds, which are sigma bonds. So do not forget to include them also. So once you have this drawn out, you can do a quick calculation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 sigma bonds. A polymer that's formed, what is the monomer that will produce this polymer? We try to look for the repeating units. We can see that this is the repeating unit, and we form back the monomer. This is an addition polymer, so we will know that there's a double bond between these two carbons at the start. So a double bond, 3 hydrogen and 1 chlorine. (23) We have this ester, and how can we actually create this ester? Sometimes you can get the clues from the name. This is your alcohol, so you actually need 2-methyl butanol, and this is your acid. You need ethanoic acid. Okay. If not, you can do your hydrolysis. You cleave your ester bond. This will be the acid, COOH, and then this will be alcohol. You add a H here to form back your alcohol group. And then you compare your species. You have your ethanoic acid and your 2-methyl butanol here. (24) Burning X gives carbon dioxide and water only, and it produces steamy fumes with PCl5. PCl5 will react with OH, that means it contains alcohol group, or it reacts with the OH in a carboxyl group. So maybe we have alcohol, maybe we have acid, we can't be sure. But X doesn't give us any products with 2,4-DMPH. That means we know for sure it's not a ketone or not an aldehyde. So which one can we know for sure with certainty? We can't tell whether it's acid or not. We can't tell whether it's alcohol or acid, but we know for sure since it doesn't have a product with 2,4-DMPH, we know for sure it's not an aldehyde. Q25 is also quite a popular kind of question. Ethanol, we oxidize it and then we take distillation to extract the product. In other words, they're telling us we get aldehyde as a desired product and not an acid. The yield is 70%. So how do we find the mass of the product? I'll do a simple equation. This is our alcohol. This is our aldehyde that we desire to have. So we start from 2.3 grams. We know that only 70%, we can see it as 70% is changed to or successfully converted. So 2.3 multiplied by 70%, 1.61 of alcohol was converted. Then we convert to the moles, we divide by MR. This is the moles of alcohol successfully converted. By ratio, this is the moles of aldehyde successfully obtained. And then we multiply by aldehyde's MR, which is 44. We will get the mass of aldehyde obtained.